Hello and welcome, lazy chemist, to today's lecture where we are going to be doing some balancing with oxidation reduction reactions. Today's image is of apples oxidizing. As you can see, we have nice tasty green apples here, and we have some apples that are beginning to lose their tastiness, or at least their appeal to being tasty right over there, because they're oxidizing in the oxygen. The main reason that we're going to go ahead and balance with oxidation reduction is because sometimes using oxidation reduction reactions, they can become hard to balance. And by learning how to balance specifically the charge first, that's something that we could use to help us balance some harder equations easier. And there's also some more complicated balancing that when you do some of these processes in acidic solutions, you want to add to a balanced equation the fact that you have an acid or you have a base. And today's lecture is just kind of getting through some of the basic processes that are involved with that so that we can go ahead and simplify it easier. In terms of what you're expected to do in this section, you're expected to be able to break apart a reaction down, both in terms of the particles and the charge, and using the charge to go ahead and work your way through a equation and balance it using the charge as the primary force for balancing instead of using your particles, which you've done in the past. And that's really what's just expected of this section here. So usually what we have to do here in this section is we have to go ahead and break down these compounds into half reactions. All right. So for instance, this is a really simple reaction. This is solid sodium reacting with chlorine gas, and it makes 2 sodium chlorides. And our reaction essentially is sodium metal turning into a sodium ion, and we have chlorine gas turning into a chlorine ion. Okay. So here, as an example, we have a oxidation reaction. This one has lost electrons. Here we have a reduction reaction. This one has gained reactions. So those are the two reaction pathways that we're going to break it into. Okay. For the actual reaction of sodium breaking down, or the oxidation of sodium, what you're going to notice is that we're going to go ahead and write the oxidation numbers here. We usually write them right on top, and this is kind of like work, just like the process for writing the work. And we'll write Na here, turns into Na plus, so it goes from a charge of 0 to +1. And then we usually like to include that electron there, okay? So that's just kind of indicating, hey, an electron is lost here, just conserving our charge across this equation, okay? Whereas the reduction one, it's going to be very similar, where chlorine starts at 0, but we need to add 2 electrons in order to make it -1, okay? And again, this is the reduced one. Notice also that you can check the charge. The charge has been reduced. It's no longer 0, it's -1. Okay. Okay. Some things to help us balance this out. Electrons that are made in the oxidation process are going to be used in the reduction process. For oxidation to happen during a chemical reaction, reduction has to happen as well. You're not going to get this coming out of nowhere. The number of electrons made in oxidation must equal the number of electrons acquired in reduction. So we have to have the same amount of electrons. The transfer of electrons changes in oxidation states. Basically meaning that you're going to have some change in an oxidation state if an oxidation reaction occurs. Oxidation reduction reactions are going to be any chemical process in which an element undergoes it. Okay, So, these are just some basic terms. Mainly the big thing to watch out for with these things is that the amount of electrons on one side that are going to be gained have to equal the amount of electrons that are going to be lost. Okay. This right here is an example of a half reaction. Okay. In this case, we have copper, and it's reacting with, this would be nitric acid. And when we balance it out this way, what you'll see is that we end up needing 6 electrons here. We have 6 electrons on this left side here. You'll notice that we have this nitrate ion going from a +5 state to a +2 state, so it's being reduced. This one here is being oxidized. And then we end up putting our two reactions together. What you'll notice, though, is that since we have 6 electrons here on the left and 6 on the right, that those will end up getting canceled out. And this is kind of like a full filled out version of the kind of reactions that we're expected to be working with throughout this unit. Okay. There are some things to note. If you do go through one of these and you find out that, hey, when I'm making out my oxidation states, here sulfur ends up being +4. On this side, it also ends up being +4. That's a non-redox reaction. So just be aware of that. If nothing changes in terms of the actual oxidation states, you don't have a reaction. Another example that's written here is sodium chloride and silver nitrate. Even though that's a precipitate reaction and we have an exchange of the metals going on right there, that is not a redox reaction because all of the elements that are involved here keep their same oxidation states. Okay. In redox reactions and with covalent bonds, we're going to go ahead and use the same rules from before with our covalent bonds. So for instance, where we ended up saying that nitrogen's oxidation state is based off of oxygen, we're going to use that as our oxidation state, even though it is a covalently bonded structure. So they use this example right here. This is actually a covalently bonded acid right here. Chlorine doesn't have enough to take all of the electron away from hydrogen. But we're still going to go ahead and say, oh, okay, well, chlorine's stronger than hydrogen, so therefore chlorine is going to have this oxidation state of +1, and hydrogen's going to, or -1, and hydrogen's going to have one of +1. So just be mindful of that as we go on, that they don't actually have that full-on oxidation state, but we're going to treat it that way. And this just goes really far deep into it to a degree that we really don't need to worry about much of these, because what we're only doing is tracing and using charges to help us balance out here. Okay. And so what we're going to do here for our half reaction balance method is that we're going to go ahead and assign oxidation numbers to all of our atoms. We're going to balance our half reactions separately for mass and for charge, and then we're going to go ahead and add that together. Okay. This right here is essentially what I would like to call like the lazy Bradley method. And what I like to do is I like to write out the net ionic equation for each reaction, figure out the oxidation states for the half reactions. Okay, so I figure out everything's oxidation state, balance the atoms of each half reaction, balance the charge, and when I go through and balance, what you'll see is that we'll end up adding, if we have like a case where we have water on the left side of an equation, but we don't have it on the right, what we'll go ahead and do is we'll just go ahead and add some water on the right. And the reason that it's going to work out is that our goal is going to be to try and cancel the waters that we, add on one side or the other. And we're kind of using it as a go-between, okay? When we're balancing out equations in this method, what we're actually doing is we're trying to cheat using charge. So when we add water to one side to help us balance the oxygen, it's more so that we can go ahead and hopefully cancel it out at the end. And then if we end up adding water and we have too many hydrogens, then we'll use an H plus to go ahead and get rid of the extra hydrogens when we're balancing out the actual atoms. Okay. For number 4, we're going to go ahead and balance out our charges with electrons. Okay. So that means that we're going to have, an electron charge on the top one and an electron charge on the bottom one. We're going to ensure that the electron charge ends up being conserved. So that means that if we have 8 on one side and 4 on the other, we're going to multiply the side that has 4 by 2 to ensure that they're at the same level. Okay. And then we'll add the reactions together, and we're going to get rid of anything that, we can cancel out. Okay. And I'm going to show you guys a more formalized version right here. This here is writing out the half equations, or writing out the equations, and they've already broken it down into the ionic equations here. Okay. So we have hydrogen sulfide, hydrogen ion, nitrate ion, 2 hydrogen ions, a sulfate ion, nitrogen dioxide, and water. Okay, they're assigning the oxidation states. Okay, so sulfur is -2, hydrogen's +1 here. It literally has +1. NO3 minus, this is going to end up being +5. This is -2. +1 here. There's 4 of these. It has a -2 charge. It should be +6. And, going forward, +4, -2, +1, -2. Okay. And then we would go ahead and look, and you're going to check each time. You want to make sure, has there been some sort of oxidation reduction? Okay. So the NO3 here, the N, has gone from a +5 state to a +4. Okay. So this one has been reduced. The sulfur has gone from a -2 here to a +6. So this one has been very much oxidized. Okay. And then anything that does not actually change, we go ahead and get rid of. So we get rid of the things that aren't doing anything, things that aren't being oxidized here. H we can get rid of, H2O we can get rid of. They're not doing anything in this reaction right here. Okay, so our H's we get rid of, H2O we get rid of those as well. Okay. We're going to write out the balanced half reaction. So here we have the hydrogen sulfide, and it's going to a sulfate ion. And this one right here is the one for reduction. And that's the nitrate ion going to nitrogen dioxide. Then what we're going to do is we're going to go ahead and balance out the atoms. Okay. In particular here, we have 2 things that are in error for us. We have 4 oxygens here, but we have no oxygens on this side. Okay, so that means that we're going to have to add in some waters. Okay, since there's 4 oxygens here, we're going to add 4 waters here. Okay, and that'll give us a total of 8 hydrogens here, with this water, plus the 2 hydrogens here. Therefore, in order to balance it, we're going to make this 10 hydrogen pluses, so 10 hydrogen ions, over on the right side. Okay. And the whole reason that we do that is just to keep the atoms balanced there. Okay. So we're balancing our mass first. Then what we'll do is that we'll go ahead and balance out our charge. Okay. So here, everything that's on the left side is an even charge, And the right side, we have issues. Okay, we have a -2 charge, we have 10 over here, so we have essentially +10, which means that we need to add in 8 electrons in order to make the charge equal. Okay, and that's what we do here. So we're going to balance out the atoms first. Then we're going to go ahead and balance the charge directly afterwards. We're going to do the same thing for the reduction reaction now. Okay, so the reduction reaction, we have NO3, NO2, we're short 1 water. Okay, we have to go ahead and add 1 water. When we add 1 water, we're now going to be short 2 hydrogens, so we have to add 2 H pluses. Okay, we're going to go ahead and then balance the charge. We have -1 plus 2 H pluses. We need to have 1 electron on the left to go ahead and balance that out. All right, so this is going to be the final reaction for this side here. Then what we're going to be looking at is actually the charge difference. And in particular, it's going to be the fact that we have 8 electrons on the top reaction and we have 1 electron on the bottom, which means that our bottom reaction, we're going to need to multiply everything that's in that reaction by 8 in order to go ahead and balance out our electron difference. Okay. So then this is going to end up being this reaction as is. And then this one, we just multiply everything by 8. 8 NO3, 16 H pluses, 8 electrons, 8 NO2, 8 H2O. Okay. Then what we'll do is we'll go ahead and cancel out everything that can be canceled. So here on this left side, we have a lot of things going on. But we can first of all cancel out 4 H2O with the H2O that's on the right side. Okay. So we go ahead and reduce. We've removed 4 from this side. We'll remove 4 from this side. Okay. And then we can go ahead and remove 10 H pluses from both sides, which will leave us with 6 H pluses. And finally, our electrons will cancel, which is our main goal. We want to go ahead and cancel those electrons, which means that we'll be left with this reaction right here. And this reaction right here. Come on, get rid of there. And this reaction that's at the bottom here has our NO3, it has our hydrogen sulfide, it has the acidic portions, it has everything that we need for this reaction to go forward. All right. And then it's just having you combine the ions. I would be perfectly fine if you left it in, the non-ionic form, but all right. And then this is just some language thing. Reducing agent is a substance that has the potential to cause another substance to be reduced. So it's usually the thing that gets oxidized. And oxidizing agent is going to end up being the thing that reduces. So for instance, in this case right here, the nitric acid would say to be the nitric acid is reduced, therefore it's the oxidizing agent. The H2S is oxidized, therefore it's the reducing agent. Okay, so just some annoying little language type things there. Next, we're going to briefly talk about the strength of oxidizing and reducing agents. And this has to do real briefly on the relative potential for it to gain or lose an electron. Okay, So this is the reactivity series, and this is kind of indicating how easy it is for these different compounds to lose electrons. And so the ones that are up here are more likely to be reducing agents, whereas the ones that are over here are more likely to be oxidizing agents. Because these will get oxidized and these will get reduced more often. Okay. And then a couple of things, the further they are apart, the more likely it is that you'll get an oxidation reduction reaction. And just basic things right there. And this is just another chart that ends up showing it. In particular, just showing like the difference between the elemental state and then like the actual oxidizing agent state. And I think that actually goes a little bit too far beyond what we need for this course for right now. You can also have some cases where you have auto-oxidation, and this can happen in something like a lot of peroxides that end up having that extra oxygen group right there, that extra charge going on there. What'll happen is that they'll actually go ahead and auto-oxidize into O2. And this is a case of auto-oxidation where the oxygen atoms go from a charge of -1 to -2, and that 2 of the oxygen atoms get sloughed off and they end up having a charge of 0. So that's an example of auto-oxidation right there. Okay. For the most part, what we're concerned is for you being able to work with and balance the half reactions with charge. Okay. Remember that we're concerned with the actual elements that are undergoing the redox reactions, and then we try to go ahead and just balance it out from there. This is going to go ahead and close us out for today's lecture, and you should have a couple of practice problems on this one here. We're going to have a day for concept for this lecture, and then a day just where we go ahead and practice balancing out half reactions. I hope this will lead you to be able to shortcut on at least some balancing reaction problems. And as always, remember, stay lazy.